Testing, 1, 2.
Zoom recording. Okay, I've turned recording on again. Rob, welcome. Do you have access to video as well, or the screen sharing aspect of this as well as the audio?
I don't at the moment. I'm actually just pulled over. I'm driving, but I don't know how successful it's going to be for me. I keep having to tap to speak, so we'll see how we go, hey?
Gotcha. We'll give it a go, and I should be able to record this. I've got a whiteboard open as well, so we can look at this a bit later. So let me go ahead and get started. Let me close a couple of windows here, make sure I'm in the right spot. Strange. Okay, I'm not going to worry about it. You guys can hear me, so we're good. Did we lose Rob? Rob, are you still there?
I'm still here. I think my microphone automatically mutes, which is probably a good thing as I'm just about to start driving again. But
okay.
If there's anything, I can see I can see your screen. If that's any good, I can see it, but I just have to swipe between that and then I'm speaking. I have to swipe to another screen to unmute my mic. So
I'll let you head back in, and I won't be expecting any comments here because I know it's hard while you're driving.
Perfect.
Let me start with the overall premises of statistics. I mean, the basics of statistics, most of us are probably familiar with. If you want to know the probability of something happening, you take the number of ways that it can happen divided by the number of possible ways that anything can happen, and that's your probability. And for things like rolling a die or flipping a coin or picking a winning lottery ticket, that works reasonably well. Where it gets interesting is when you're looking at more complex probability events, like large numbers of events or more complex events with varying distributions. And in these cases, the thing that they mentioned briefly at the beginning of this whole topic, but that is really very important, that I think it's very important to emphasize and restate, is that all of these things are models. The standard normal or a normal distribution is a model. The exponential or Poisson distribution is a model. The chi-squared distribution is a model. And there's nothing requiring reality to exactly match that. But what they've found over time is that there are a lot of things that match this really, really well. And so these statistical calculations that can be done, if the data happens to match one of these models, do a very good job of approximating what happens in real life. And so they talk about, the desire to kind of seek significance if you're close to it. If anything, quite the opposite. If you're getting a result that's marginally statistically significant, it may or may not be something you want to base any decisions on. But basically, the statistical test is what it is. And if you choose a test, you should stick with it all the way through. And that's what they're talking about in some of the earlier sections about deciding, okay, make your decisions up front. What alpha level you're going to use, what variables are you going to use, how are you going to go about it, and don't change midstream because then you're introducing bias. So that said, the first and most common statistical distribution that is used for a wide range of things is the normal distribution. That's the bell curve we've all heard about and know and love, and it's got a really complex exponential formula to it that nobody here needs to understand. But the neat thing is that if you do certain integrals with that standard normal curve, some really convenient things happen. You can very easily add, subtract, multiply, and merge different normal distributions into a combined normal distribution. When you're looking to tell whether a particular value is, the probability that a particular value in a normal distribution is above and below a certain percentile, you can use the normal distribution to do that. And you've seen things about the Z table. There are Z calculators out there. If you have a good scientific calculator, it probably has a Z function built in, either inverse normal or normal CDF. that will tell you the probability associated with a z-value. So the long and short of this, and I'm going to draw some stuff on the screen here while we're talking, a z-value is nothing more than the number of standard deviations you are away from the mean. So here I'm going to try and draw a normal curve. Didn't fail too miserably here. It's not quite symmetric, but so in the middle you've got a mean. And here, let's say our mean is, let's say we're looking at the average height of men in Australia. And I'm going to say that that's, I guess I ought to put it in metric, shouldn't I? Well, I can't. I'm putting it in 70 inches because I'm not good with metric. Knowing what that is in metric anyway. I'm going to fix this a little bit. This and that, and there we go. And let's see the standard deviation in their heights. Actually, I can convert this to metric. Under 75 centimeters, let's say. So here we are. Average height of 175 centimeters, that's our mean. And let's say our standard deviation is 10 centimeters. So it'll be spread out appropriately based on that. Here we have our standard deviation. And as you've seen, oops, I gotta change this back now. 68% of the values are gonna be within plus or minus 1 standard deviation of the mean in both directions. That means that 68% of the heights of people will be between 165 and 185 centimeters of men in Australia. If I go an extra standard deviation out from here, I'm going to get 95% of all those values, and it's going to give me a range of 155 to 195 centimeters. That'll be a range of 95% of the people, and so on and so on. And if I want a specific value, I can look up a standard normal curve. Why don't I pull one of those up while I'm at it? I've got a good one. Yeah, let's do this one. Well, that's pulling up. So there's just a variety of different calculations you can do here to convert between values of height, what they call z-values, which is how many standard deviations away from the mean you are, and probability values. Let's say that we have somebody who is, let's say we get Shaquille O'Neal, and he is 195, now say 200 centimeters tall. Well, we can convert, there we go, his height into a z-score. So that z-score is going to be simply the number of standard deviations his height is above the mean. So it's x value minus, see if I can get that symbol in here. There it is on U. Come on. And we divide that by the standard deviation. And that's going to be our z-score. It's simply how many standard deviations are you away from the mean. On the other hand, if I wanted to get the average mass and did a sampling of the average mass of earthworms in a field in Kentucky, I could also make a standard, a normal curve based on that, and it'll look different. Maybe my mean there is, I'll do the same thing here. Let's not reinvent the wheel. Let's copy this thing. this thing. Now perhaps my mean is call it 20 grams with a standard deviation of 1 gram. So maybe this is a much narrower curve, still a normal curve, but it's much narrower than the other one was. So my values here are going to be much closer together, but they still encompass 68% of everything. So how are you guys with normal distributions and z-tables and things like that? Is this a topic that you're mostly familiar with?
Yeah, for me, this is yeah.
Sorry, go on. Just quickly going off mute here. Yeah, the normal distribution thing works for me, and the standard deviation. So thanks for that.
Okay, so I'm going to move on from this, but the key is you can convert this into what's called a standard normal distribution, which is just the mean is 0 and the standard deviation is 1 standard deviation. And a lot of other things are based on this. A lot of the other statistical tests, not the Poisson distribution, but a lot of the other ones are based on the idea of something like a normal distribution, where you're calculating some kind of a statistic and looking to see how far out from that you're going to get. It may not quite be like that, but it's very similar to that. For example, the student t distribution, if you have too small a number of items, like this test is only good for means up to 30, for 30 or more data points. If you have less than that, and you have data that's roughly normal, you can use a t-test, which is exactly the same as a z-test, except it just uses a t-distribution. The t-distribution is going to be a little bit narrower. It's going to look more like a binomial distribution, which, if you recall, involves just binomial data calculations with probabilities. And so it's going to be a little bit more spread out rather than the normal distribution, because there's a greater probability of outliers in the t-distribution. And so with that one, you have to calculate exactly how many degrees of freedom there are, how many measurements you have, -1, and use that to determine which curve you're using. And usually it's only easy to calculate on a table something like the 95th percentile or the 90th percentile or the 99th, though there are calculators out there that will allow you to calculate anything if you want to. So before I continue with this, with some of the other tests, Chunchek, let's start with you. What are some of the things you have the most questions about in the statistics section so far?
For me, it's really more, understanding when to use which type. I mean, there's a cheat sheet for it, but which has all the purposes of the different hypothesis tests, or like setting up the confidence intervals. It's a matter of really seeing more examples of, okay, here's a scenario. What test do we use? What should we consider? What are some of the gotchas or things that we need to look out for? I guess that's it, right? Because none of the calculation is really rocket science. A lot of it is looking up tables or plugging numbers into a calculator. But with the 12, 13 tests that we've been introduced, I feel like I'm in a bit of a forest in terms of I've got so many trees, I don't even know which one to look at.
Gotcha.
Sometimes. So that's kind of where I struggle the most. Once I can decide which test to use, whether it's a z-test or the t-test, whether I should use 2-sample versus paired sample, I think I'm good to go. But deciding what it is what I'm struggling with the most.
And how about you?
I'm probably in the same boat as Chunchek, really. I think it's just overwhelmed. There's so much information in this module that I just kind of I've got to the stage now where I'm just frantically just trying to get through the module, unleash the exam, and then just try and get to work on understanding how I answer the questions. It's impossible for them to test us on all of the modules and all of the content, but ideally I'd like to understand it. That was kind of the whole purpose of doing this in the first place. And I just it's the same as Chinchek, really. I just don't really understand enough about when I would use what table for what purpose, and when it's a population or when it's an interval, or I just find it quite confusing. I don't have any practical way of doing it. So that's kind of those are my challenges.
And that's the real takeaway from this whole section is understanding which test does which thing. If you don't remember all the details of when you must use the t-test versus the z-test, that's not as big a deal. You've got to look it up when the time comes, and you can do that. But it's about knowing, okay, these are the options available to me and the types of circumstances where I would consider these tests. When the time comes, you can kind of look up how to use it. You don't have to have all this stuff memorized. There really are 7 different tests that they have talked about here. The Z and T distribution all are related to either means or, just for the Z table, proportions. If you're trying to determine what a range of values would be and what likelihood there would be of a certain value given a particular mean and standard deviation, or the same thing with a proportion. What's the likely range of proportions given certain amount of information? If I sample 1,000 people asking who they're going to vote for in the next election, if I get a certain result, I can expect, as long as that sample is not biased, that I'm going to have a value within a certain range as long as it meets the criteria for the z-test. With proportions, you can't do the t-test in that case. For the t-distribution, it's the same thing, but only when you don't have enough data or you can't estimate the standard deviation with the sample standard deviation S. And that happens either when you have too few things or when you have 2 sample distributions or paired values. So let's talk briefly about paired values versus a 2 sample distribution. Let's say I want to run a test to see how effective a blood pressure medication is. Well, I'm going to give this blood pressure medication to maybe 50, 100 people. Now, is it sufficient to just measure the blood pressure of all these people after I give the drug?
No, you give it before, right? Because you want to know whether it changes the BP.
You want to see what changes. So because you're looking at the change, that is an example where you're looking at the difference between 2 values. What you really care about is the difference. That's a paired test where you're looking at pairs of data and comparing them. What was the result before and after I applied this drug? Or if I have 2 identical twins and I give them both some kind of a test, but one of them had some kind of a treatment applied to them, what is the result of one versus the other? That difference, we're just looking at the deviation in the difference. And in that case, you've got to use a t-test because the deviation in the that sample is not an accurate description necessarily of sigma. Now, that's not that big a deal. In reality, if you ran a z-test on those values instead of a t-test, if you have enough sample points, it's not a huge deal. Like they talk about how if you have 100 data points, you really should use a student t-test instead of a z-test. It really doesn't matter that much. Once you get past n equals 30, the difference between a z-table and a t-table is almost nothing. So it's not as big a thing. On the other hand, let's say that we picked 2 random groups and we wanted to look and see if the average price of a house in neighborhood 1 is different from the average price in neighborhood 2. In that case, we could be looking at a 2 sample z-test. We're looking at 2 different distributions, and we're trying to compare the differences between those distributions. Or here's a better example. let's say we wanted to estimate the average difference in height between men and women. And maybe we can come up from a sample with the mean and standard deviation of heights for men and the mean and standard deviation of heights for women. Well, what they said is that you can't reasonably estimate the difference in the population deviations using those two values. I get what they're saying. I would say that you could probably do a decent job of it, but they want you to use a t-test there because it's two different distributions that you're comparing, and you're comparing the means of those different populations with two different samples. So that's an example of how you'd use a paired distribution versus a two sample distributions or a double distribution. It's a matter of whether you're looking at the same individuals in one case or the other, if they're paired up, or if they're not, if they're both supposedly random samples that are representative of the general population. The rest of the tests are much more different, and I want to spend the rest of the time talking about those. The one that is the most different is the chi-squared test. That test allows you to look at categorical data and decide whether categorical data is unusual in that it doesn't, it shows a difference between different categories, or whether a particular set of categorical data meets an expected distribution. So, for example, let's say we wanted to see if there's a difference in the likelihood that men like to watch the Super Bowl versus women. We could do a survey of men and women, get the number of people of each in the survey who liked watching the Super Bowl, and use those values with the expected values if they were equal to see if the differences are so great that you can say, yeah, men like watching football more than women, or women like watching football more than men. One of the things they say in the class that I actually kind of disagree with is that you can't tell whether whether one is greater than the other. If you use a chi-squared test with two values, like two categories in both directions, I think you can tell. But normally you don't use a chi-squared test like that. You use it when you've got 10 different groups and 3 different groups, and you're looking to compare larger numbers of groups. And in that case, you don't know which one's causing the variance. You just know that there is something that's different from the mean, and you can use things like confidence intervals to get a better feel for which one is more likely to like a particular thing or to meet a certain criteria. The goodness of fit test is the one that matches a particular distribution. That's the same kind of thing. If I wanted to say, hey, I think that what's a good example of a goodness of fit test? What do I?
Racial distribution in a neighborhood, for example.
Yeah, I was trying to avoid racial distribution, but
sorry.
Let me, it's okay. There's nothing wrong with using that. I just didn't want to use it. Let's say the percentage of people of certain ages who like going out for a run, and our premise is that there's 20% of those under 18, 40%. Actually, hang on, this is not right. It's got to be an exclusive set of it's got to be an exclusive list. What do I want to do here? Yeah, so the distribution of runners in the Boston Marathon by age, that 20% of them are less than 18, 25% of them are between 19 and 30, 25% are between 31 and 40, and so on and so on. And you take the actual numbers and you can do a chi-squared test to compare the distribution with that expected distribution to see if it meets or does not meet that value. So the first one to look at is if it's categorical, you want to go straight to a chi-squared test. They call proportions categorical. I call those a different thing. I mean, so yes, proportions are categorical. It's a yes/no answer, but you're looking at the proportion, which is a numerical value. That's something you use a z-test for. But as they also said in the class, you can use a chi-squared test to check on a proportion. So I could use a chi-squared test to check a simple yes/no proportion. It's just a two-value chi-squared test. It's kind of like using a sledgehammer to swat a fly, but it's doable. Other than that, the next one, there are two others that are really significantly different. One is the Poisson distribution. Actually, I'm going to do that last. Next, I'm going to talk about the Anova distribution. It's a distribution of quantitative values to analyze the difference in variance between multiple things. So let's say I want to know whether there's a difference between 4 quantitative values, maybe the average home price in 4 different neighborhoods. I can put all my data in for these 4 different neighborhoods and see if there is enough of a difference between the prices to justify that. And it's not going to necessarily tell me which one is greater or less than it. It's going to give me an overall analysis and tell us, hey, these values do or do not match the premise that all the values are the same. So whenever you're looking at more than 2 quantitative values without categorical data, then that's when you use an Anova test. The Poisson distribution is the most different from the rest of them in that it's not the kind of test where you're seeing how far something is away from an average. The Poisson distribution is about frequency of events. So it could be how often trucks show up or cars show up at a drive-through, or it could be how often customers walk into a bank, or how often a Geiger counter ticks under a certain level of radiation. And you can estimate, based on this distribution, the probability of a certain number of people coming in the door or showing up or events happening based on that distribution. So the big thing you're looking for when they talk about a Poisson distribution is some kind of time-based sequence. How frequently or how many people per unit time. There's going to be a rate in any problem that involves a chi-squared a Poisson distribution, a rate of arrivals or a rate of events. So, for example, if I want to know the probability that at least 20 people show up in 15 minutes, and the average rate at which customers show up is 1 person every minute, that's where I'd use a Poisson distribution, and that'll kind of give me the information I need. So it kind of summarizes most of them. I didn't talk about the binomial distribution because that's more objective. It's just got an equation to it, and you can use it when you know the exact probability of something and what's the chance I get n results out of m or m results out of n of an event happening. What do you guys have questions about?
For me, it's still probably the same thing, right? I'm not sure how they're going to structure the questions in the exam, and I understand that we have a double exam, double the benefits, and then just kind of like staring at it, going, I don't kind of know which way to turn. But I guess that's kind of a function of the fact that I've struggled with this module all the way through. It's not really a natural thing for me. One of the questions, which is really left field, Kevin, but well, first of all, I appreciate you taking the time out to do this and share your knowledge and information. Secondly, what has got you to this stage with statistics? Like, what's been in your life? Did you study this at college, or is it something you've had to do as part of your job, or is it a personal interest? I'm just trying to see within your life, how has this become relevant? And that's what I'm struggling, if I'm honest, with this whole subject is I don't think I'll ever use this.
Yeah.
So that's my question.
It does come up in, and I can talk about specific jobs and how it applies to them, but I actually did not have this in college. Most people do. A lot of people are surprised that I haven't. I have taught and tutored this for more than a decade. I taught myself most of it. Probability and statistics is just natural for me. I think that way. I like thinking about data and hey, okay, what's really going on here? When I see a particular result, what does this mean? So, to answer that question, it's something I've studied on my own and that I have a good understanding of because of that. And I've spent a lot of time working on it. I've tutored a lot of people in statistics and probability, and even stuff that goes beyond this into some things called non-parametric tests and weird stuff that they go into in certain types of advanced statistics classes. But the basics are just this. What does it mean when you say something about data? For example, let's say I flip a coin 100 times. If I get 50 heads, well, that's expected. What if I get 47? What does that mean? Does that mean that this is a bad coin? And I think all of us would say, well, no, that seems pretty reasonable, right? Well, what if I get 20 heads out of 100 flips? I think we'd all agree, well, that's very unreasonable. That's something's got to be wrong there. Now, I say gotta, but it doesn't have to. I mean, if I flip a coin enough times, eventually I might get a result where there are 20 heads out of 100 coin flips just by random chance. And that's the whole type 1, type 2 error thing, which, by the way, I get backwards all the time myself. Which one's which, and I've got about a 50-50 chance of getting those right, unless I look at it. But the question is, at what point does that break? And statistics answers that question. There's a mathematical way of saying, okay, when you get beyond about 40 heads or 60 heads out of 100 coin flips, that's unusual to a 95% confidence level. That is, if I flip a coin 100 times, there's a 95% chance I'm going to get between 40 and 60 heads. The same thing applies for all sorts of other data. Hey, if on average, customers show up at Taco Bell at a rate of 1 per minute at the drive-thru, so I'd expect to have 60 cars an hour, I'm going to plan on my staff based on that rate. Well, what's the chances I'm going to have 120 in an hour? What's the chance that I'm going to have 90 in an hour or 10 in an hour? And you can estimate those probabilities using the Poisson or exponential distribution. It generally works pretty well when talking about things that are random rates of arrival. It works pretty well in those cases. So it's just a way of thinking about it. It's like, okay, there's not just a piece of data, but how much should we expect this to spread out? What's the likely result if I did this randomly a whole bunch of times? Rob, what do you do for work?
I work in media and advertising on the strategy side. Okay,
so one place this would come up, social media. What's the expected number of people I will have as a response to a particular campaign? If I try A/B testing on campaigns, how do I know that campaign B was better than campaign A? If I got 12,000 responses from campaign B and 10,000 responses from campaign A, is that statistically significant? Or is that just something that can happen randomly? And it's not something that is absolutely essential to the job, but it's a way of thinking about that where you can say, okay, yes, this number was higher. Was it higher enough that I can say, hey, I should use this method instead of that method? And so that's what people are looking at when they look at statistics in a management perspective is, do I see a trend here? Is there something I can make a reasonable decision about? Or is this just random noise? Because you don't want to just chase random noise with your business decisions. It leads to bad decisions. You want to make your decisions based on something that is pretty certain to be the result of an actual reality, not based on a random toss of a coin.
Yeah, cool. So specifically on that, that's an interesting example, because lots of the stuff I get involved with is around multivariate testing and testing creative A against creative B, or font A against font B, or whatever. And again, doing that at a significant rate, and trying to get some inferences that are valuable to the client to say, actually, you should use the size 14 Times New Roman red font in the top left-hand corner because that's got the best click-through rate. And so I kind of get that. But I suppose back to my earlier question is, I don't know as I'd necessarily know. It's got a time limit. Can you still hear me?
Yes.
Sorry, it just came up on my screen saying meeting's got a time limit. I don't know, I necessarily know which test to use and why, like whether it's that's kind of my question. So as an example, in that scenario, I'm testing two creatives. They have two different colors, red and blue seems to be performing better. How would I get, like, obviously things like click-through rates and which one's higher, but what sort of tests when would I use, like a T-square, a Z, a chi, whatever it's called, like chi, whatever it's called? Like, I just don't know when I would use them.
Yeah, and that's what I just talked about for a bit. And, there are specific circumstances for each of them. And that's the thing you really want to be familiar with is, okay, when do I use each one? The chi-squared is for categorical data. If, you have people choosing, 1 out of 5 different options, and you want to see, hey, is there a difference between men's and women's preferences on these 5 fonts? You use a chi-squared test for that. On the other hand, let's say you had those 5 different fonts for men and women, and you had a number score 1 to 10 for each of them, and you wanted to know if there's a difference between the scores on any of the different fonts for either men or women. That's where you'd use an Anova test, because you have 10 different numerical values, the mean score for each of these fonts. So it's subtle, right? I mean, doesn't sound like it's a different thing, but it's just a matter of how the data is collected and what type of test you do based on the type of test you've run. So I hope that helps. And I have to wrap up here pretty soon because it's getting late and I've got a long day ahead of me tomorrow. But do you guys have any last questions you'd like me to cover before we wrap up?
Thanks for that, Kevin. I really appreciate it.
Yeah, that last explanation was actually really, really helpful just now.
Good. I'm sorry it took so long to get to that, but I hope that
no. Everything else has been helpful as well. But I think you just sparked a light bulb in my head with what you just said a minute ago.
That's an important point, that you can measure the same data 5 different ways. And if you measure it one way, you should use a chi-squared test. If you measure it a different way, you should use an Anova test. If you measure it yet a different way, you should use a Z test. It's just a matter of how you measure it. And depending on how it was measured will determine what type of test you're supposed to use to analyze it. All right, well, have a good rest of your day, guys, or evening, as the case may be. And
thank you so much, Kevin, for taking the time out. I really appreciate you doing that. It's very kind.
My pleasure, and hopefully I'll be able to join on Monday. It's a holiday here in the U.S., so I'm not going to have work in the evenings for a change. And looking forward to catching you all then.
Very good. See you next week, Kevin. Thanks a lot.
Thanks again, Kevin. Cheers. Cheers. See you, Chen.
Cheers.
See ya.